for the presentation. I'm going to present part of our work which was done within the context of a project in Finland. I come from Åbo Akademi University in Turku, Finland. And this project was about future electrified ships. Basically, it was a study to assess the business model after electric ships, and also the feasibility of building software twins, not only for the ship content or the ship software, but also for the whole process of whole pipeline of the shipbuilding. And the study, or this presentation, is titled Transforming or Exporting PLC Control Logic into FMUs using an open source approach. Basically, sorry for repeating again, but this is the traditional step from the shipyard point of view for shipbuilding. It starts with design, construction, and life cycle. In the design part, there is a traditional integration test where most of the cases this is done by suppliers arranging meetings, physical meetings, and trying to connect their system together. I mean, what Severin mentioned today, that this approach has moved on for some shipyards, but for some others, not everybody is yet there to the modeling in the traditional integration test. And then we have the constructions with sea trials, the commissioning process, and then the life cycle where continuous update happened. I mean, this process is very rigid. Sometimes error and problems are defined in the commissioning phase, where recoveries are very costly, and the time frame, time schedule, it's limited. So the idea is to, sorry, this is not working. Yeah, I have to be close here. The idea is to provide a digital line which augments a bit the physical traditional process of shipbuilding, which starts with very, very early modeling and simulation of integrating the ship subsystems by having models which are provided by the suppliers. And then on the second phase of this digital line, we have adjustments, optimizations, increasing of the efficiency of these components. We can do sizing and additional modifications. And then on the last part, during the ship operation, we can have continuous testing of software updates, which might be linked to new features implemented in the software systems of the ship. And this is very important to do it online, especially in this case, because we might get error that that if those propagate to the real ship, which is in to the real software which is on the ships, it might cause delays or disruptions of services from the ship, which is for the clients, the ship owners, it's very problematic. And from these digital lines, every actor which is involved in this process would benefit. The shipyard, of course, would benefit because it can increase the efficiency of this pipeline of the shipbuilding. For the classification societies might, of course, benefit from this process because it might be easier to assess the class of a ship or to give the approval. For the client, which will have a better ship tomorrow for operations, and in order to avoid any disruption of service, which is very, very costly. In a real use case proposed in this project, we considered the integration task at the shipyard site. We discussed today that the shipyard is the real integrator of many components, and components are provided by different vendors. And we considered a case where we have like components provided by Wärtsilä, such as the propulsion, the EMS or IAS, and a company of Wärtsilä, which is Corvus, which provides the battery and the battery management system. Of course, since all these components comes from a single vendor, it's easy for them in-house to integrate the interfaces between them, and everything inside this box will run smoothly. The problem is, how do you interface that, and how do you integrate with another subsystem, which is important for the ship operation, which is the HVAC. The HVAC is provided by another company, let's say CATC from Sweden, which provides the automation and the physical PLC for running the HVAC. And the problem is, how do these two subcomponents among the many subsystems of the ship, which a shipyard has to integrate, how does it work, these interfaces between these subcomponents? And the scenario we were testing in this project is, for example, having a single PLC. In actual RoPax ships, there are like 100 PLCs, might be, which control the HVAC, but the scenario is basically the same. The PLC exchanges command with air handling unit, which then provides airflow and conditioning to the cabins in different decks and in different zones of the ship. Basically, the PLC exchanges signals with IES or EMS, and also with HMI and the SCADA system. So this is a kind of a representation of how the HVAC system, which is represented by a single PLC in this case, interfaces with the other subsystems of the ship. The problem is that at the moment in the shipping industry, in the ship domain, there is no standard way to transfer the control logic of, for example, in this case of the HVAC, into a model which can be simulated into a bigger picture. What happens is that automation engineers, they program their PLC code into a standard environment, depending on the vendor that is going to be used, and that is simulated inside the simulation runtime, which is connected to the environment they use for developing the code. What we would like to do with this digital line is basically trying to get the control software code from this PLC program and transport it directly into a simulation environment, which might be a standalone OSP installation or SDC in the cloud. And basically this work is mainly focused on this digital delivery pipeline, noticing the problems that are faced in automation project in the shipping domain. Of course, in automation industry, this is kind of solved by now, because they use like other technology like MTP or other standards of PLC programming, which are a better, like, let's say, interface with the FMI concept. Yeah, if you go and do a research about the major vendors of PLCs and the software they provide for developing code, there is a clear lack of FMU exporting capabilities. For example, Schneider, ABB, Rockwell, Beckhoff and Vago, which we were in contact during the project, they have a really lack of, let's say, support for the FMU exporting. There is something in the Siemens with their automation studio, basically, but all of this comes under a high cost licensing for these features, basically. So the idea was like to provide an open source approach, which starts with a program built in one of the substandards of the IEC 61131 for programming PLCs, which is the usual standard they use for automation project. I say the usual because there is another standard 61499, which is used much more from the automation, from the automation industry in developing distributed control systems. So the idea would be from this standard to go directly into exporting the PLC program into a C program, matching it with the runtime system, and exporting in an FMU package, which then can be used in a simulation environment. Basically, this pipeline started from OpenPLC, which is an open source tool for testing PLC programs, and then it provides also a runtime that you can use to export the whole project inside hardware devices like Raspberry Pi or Arduinos. So the pipeline started from the PLC development project and all the way through getting the binaries for the code and getting also the interface variables for this software. So what comes in and out. And this is all wrapped into an FMU file. So the new components which were developed in this project was basically the translation from the PLC program, getting the variables and transforming the structured text code into all the way into an FMU by having this intermediate C code representation and then compilation. This is a bit more detailed workflow of how this is done. For different PLC program, you might have different POUs, and all those POUs are tested to get the input-output interface variables, and everything is wrapped by an FMU wrapper into an output file, which is file.fmu, basically. Yeah, and one problem that exists if you talk about exporting the PLC logic into a model is that the way co-simulation is run is that you have the master algorithm, which has its own time step, and it defines how the information is exchanged between the slaves, which are other subcomponents in the simulation architecture. But the way PLC works is that PLC has its own timing, has its own runtime period. And what it does basically is that you generate you create the program of PLC, and when it's translated into a simulator, and the PLC simulator, or into a real hardware, it gets a loop, and inside the loops checks if it's available any input signals. It does the computation and it provides the output and then sleeps, and then it waits for the next interrupt tick to redo again the same thing. And this contrasts a bit with the co-simulation algorithm, basically, because the co-simulation algorithm has its own time step. And it tries to involve the PLC program into doing something, while the PLC has its own runtime. And this is basically this runtime loop that the PLC logic follows. The way this is solved, or before the solution, what it produces, it's like this scenario here, where we have a kind of a simple inverter implemented with this approach. And if we simulate that inverter, provide a sinusoidal sine wave input function, and the output is kind of stepped like this, because the time period of the co-simulation algorithm does not match with the runtime period of the PLC program. And basically, in this case, the PLC program is kind of, it's too slow for the co-simulation algorithm. Co-simulation algorithm tries to provide new input, but the PLC program has not waken up yet. And when it wakes up, it sees another input and so on. So this mismatch of the periods, it's causing this trouble, basically. The idea, what we implemented here, it's kind of input into the runtime loop of the PLC program, a flag, which sends a notification if the inputs are sampled once and the logic has run. Don't wake up until you have additional inputs. And basically, with this implementation and this modification in the runtime loop, we have kind of a better stable response from the control logic. So not the one that we have before with steps, but we have kind of more smooth, apart from this fluctuation, which are related to the non-deterministic behavior of the PLC logic. Because what happens here is that when the PLC program starts running, you start up another thread in the OS. But in the general purpose operating system, you don't have kind of a deterministic guarantee that the program will run through all the period, because you get interrupted from different kind of other processes which need to run. So basically, those are optimized for throughput. They're not optimized for guaranteeing a certain scheduling execution. Yeah, and so this is kind of better, but still does not have a 100% determinism guarantee. Yeah, some simulation which were done with a HVAC system of different signals which come from the PLC and go to the air handling unit. Basically, the humidity check, CO2 level, temperature, with different occupancy rates of the thermal zone, basically. A different signal simulation run through OSP. The energy results from how much energy the HVAC system is consuming with different scenarios, basically. Limitation of this exporting approach from PLC program to FMU, basically. There is a performance overhead. Of course, now you have like higher abstraction, and it cannot run fast as like a native implementation, like we said before, in C or C++, which is kind of a limitation at this point. Synchronization issues, basically, sometimes because there is another thread spawning in the simulation, as I said before, there is this problem with synchronizing the time step of the co-simulation algorithm with the period of the PLC runtime system. So it's either we defined a very low cycle time for the PLC, so it will be able to get the new updates which are present from the co-simulation algorithm. And then with our loop approach, we kind of make sure that it runs only once the runtime for each new data that comes in input. And the deterministic limitation, basically, as I said, in general purpose OS, we don't have kind of 100% guarantee that this thread will be continuously running, because it might be interrupted by some other process. It would be nice also to test how it works with hardware in the loop simulations. So basically to interface the signals that come from an outside hardware with PLC FMUs. So basically to conclude, in the automation project in the maritime industry, so there is a clear missing integrated framework for transferring control logic into a model for simulation, basically, which, I mean, it's more advanced in other industries by having other standards and technology. So we explored different mechanisms to export this automation logic, and kind of defined an open source pipeline how to generate an FMU from a PLC code. And this approach is based in OpenPLC editor, and our pipeline can be integrated as a plugin into the GUI of this tool in order to have an FMU directly from the OpenPLC editor. we developed within this study a dynamic logic system for PLC binaries, like to provide a containerized FMUs for both types of simulation, model exchange and co-simulation, basically. And we basically demonstrated the validity of this approach through simulating an HVAC control system, which showed that it worked. And of course, there are several ways to improve, but I think it's an important first step to fill this missing gap between these two parts. Yeah, and that was kind of the end of my presentation. Thank you for listening. And if you have any question, I'll be glad to answer.
Thank you. Maybe time for one quick question.
So in the PLC, you have the main program cycle, but let's say in a Siemens PLC, you also have like OB100, that's a time interrupt every 100 milliseconds, and it interrupts the main cycle, and then it continues on the previous one. Do you have time synchronization for time interrupt cycles in the PLC?
When we export an FMU for co-simulation in OSP, basically what within our approach, the runtime period is really small. So basically the PLC code, it wakes up, it runs the computation very fast, and it shuts down. And basically this is done only once per time period of the co-simulation algorithm for the time step. And this is independent of the vendor of the software that they are using for developing PLC code. Because you might have, like, for Beckhoff, you have TwinCAD, for, I don't know, Vago, you have Codesys, and all this software are quite different from each other. In our approach, we tried to make the things like starting from open source tools. And everything, it's kind of exportable into a standalone container. It doesn't need any license or any runtimes, because if you use, for example, PLC code from Beckhoff or even from Siemens, I mean, I guess you need to have a runtime or a license in the machine used for simulation or in the cloud, for example. How can you use like FMUs which are exported for proprietary tools without any kind of licensing checking? And that's a main problem, basically, that all these vendors have their own licenses, which have problems in like running in the cloud or in any standalone installation of OSP if you don't have the right license, basically. I don't know if I answered. Yeah, we have kind of running in smaller cycles, which we are able to get the new updates which come from the main co-simulation algorithm. So it's very fast and it sleeps then, and then it wakes up when we have kind of new data. That's basically. Yeah.
If I understood you correctly, that would be something you realize that's
yeah.
As interrupts that are time-based. Because I understood you would have two cycles.
Yeah.
You can have different ones. You can have like time on pace. Yes. Yes. And I think that would be that way.
Yeah. 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 Yeah, problem.
All right, I think we have to continue because didn't you say the pizza was ordered for 4 o'clock?
Yeah, or I think we just take a quick break, but grab a last cup of coffee, and then because we have the hangout afterwards, so then we can. It will be more time for both food and drinks in a very short time. But I think we need just a small coffee, stretch our legs, 5 minutes, and then we're back. And then for the last small session.
Quick 5-minute break, and then the. Yeah, thank you again. Sorry. Quick 5-minute break, and then the last 2 presentations of the day, and then pizza, beer, and conversations. Plus. Awesome.